Hi everyone, Assalamualaikum. So before we move forward with our inferential statistics to test our hypothesis, I should tell you about analyzing the research data step-by-step process, okay? So here's the step-by-step process of your data analysis. So typically we start with identifying whether you have common method variances or common method bias in your data itself. Some students tend to skip this, but I have seen panels of master by research, especially master by research, and probably later on when you have already embarked in your PhD. And if you send papers, if you send manuscript to good journals, they will definitely ask you whether you have addressed the common method variance or common method biases. So after that, we conduct dimension reduction, sometimes using EFA, exploratory factor analysis, or sometimes we use the principal component analysis. What we're going to learn in this class is using principal component analysis. Well, sometimes some scholars, they use it interchangeably. The results of both are quite similar, but statistically speaking, it's a little bit different. Okay, and then after that, you conduct reliability tests. Why do we conduct reliability tests after dimension reduction? Reliability test, you need to conduct it after you have gotten your pilot data, right? So after you have collected probably 30 or 50, you stop your data collection and then you run reliability tests on it to ensure that the scales that you use are actually reliable, are actually consistent. Okay, we are measuring its internal consistency. And then after that, you conduct dimension reduction, right? So when you drop several items, several items that cross load, or several items that doesn't load appropriately, so you need to run another reliability test on it, right? Because your the number of items in the scale has been reduced. Then conduct another reliability test. So in your data analysis, you typically conduct several reliability tests. So after that, then you conduct your descriptive analysis. You can take a look at the overview of your respondents, and then after that, you conduct your hypothesis testing using inferential statistics. So let's move on to the common method bias, CMB or CMV, common method variances. Typically, common method variance exists because we collect our data from a single source, meaning to say that we collect the entire data from a respondent, from the same respondent. There's a lot of ways for you to be able to avoid having common method bias in your questionnaire. But in this class, we are going to test whether we do have common method variance or common method bias in our data using the Harman single factor test, right? And sometimes common method bias can also occur due to your instrument. So therefore, what is common method bias actually? It is a bias or some errors that comes from the instrument itself and not from the predisposition of your respondents. It comes from the instrument introduced a little bit of error or biases, and sometimes it's because how the instruments are worded. Sometimes it's how we organize the instruments. It can also lead to biases. Why is it such a concern for us? Because it can create a false consistency. It's telling you that probably your data is telling you that, oh yes, we have good internal consistency, but in actual fact you have biases. That's why it shows you false consistency. So these are the error. The error can manifest like this: when the data is perfectly correlated without biases or variances, you're gonna get your R equals 1. Okay, probably your R is 1. But with the existence of variances, common method variances, your data will only say 0.52. So if the data is uncorrelated and you don't have any biases, it's going to tell you that there's no correlation, 0.00. If you have an uncorrelated data but you have common method bias, your R score will read differently. Okay, so it can change or alter your study's finding. So that's why we need to address common method biases. So I'm going to show you a typical model and the Harman single factor model. Right, so this is our typical model. So we have a latent variable, a variable that cannot be seen, right? Cannot be measured directly. In order for us to measure our latent variable, we have several manifest variables. For example, a simple example would be your service quality. For you to be able to measure service quality, there are several subdimensions or several manifest variables that we call, such as reliability, tangibility, empathy, responsiveness, and things like that, right? So for service quality. Okay, say for example, I want to measure waiter's performance. I cannot just simply see the performance of the waiter, right? I can see, but how do I measure it? It has to be operationalized. So my manifest variable could be a check average. So what is a check average? A check average is an average bill per person, probably per table, per person, per couple, okay? It depends on your operational definition. Or table turnover, okay? Or the table turnover. Because if the waiter is really fast in doing their job, the table turnover is going to be high, right? The table will change customer quite frequently, right? The amount of tip that they manage to get at the end of the shift or probably at the end of the day, right? And also communication skills. So here's an example. So this is our typical model, right? We have, in this example, you only have two factors. Just now, when we talk about the waiter's performance, I have four factors, right? In this example, we only show you two factors because I don't have a larger canvas, right? But in Hammond single factor model, I'm forcing everything. I'm forcing all the items under the manifest variables to load into a single factor. If they load into a single factor and explain more than 50% of the variances, then I would have a common method bias issue. I would have a common method bias problem. If they do not load if they do not explain more than 50% of the variances, then I don't have a common method bias issue. So there's a lot of sources of biases. For example, common rater. You collect data from a single source, a single respondent, right? Common measurement context, probably the design. Because typically when we ask questions, we typically will ask, like for example, this the variable service quality. So we would have an item service quality 1, service quality 2, service quality 3. Okay, so the respondents will see 5 items measuring service quality one at a time, right? One at a time. It's not gonna be mixed or it's not gonna be jumbled up like question number 1 is asking about service quality item service quality item number 1. Question number 25 still asks about service quality number 2. And then question number 2 asks about empathy number 1. You know, it's not jumbled up like that. It's organized. So that can also introduce biases, right? So how do we address CMV? As I mentioned earlier, there are several ways to address it, both before data collection and after data collection. But in this class, we're going to test whether we do have common method bias or not, or we have issue of common method variances after we have collected the data. Right, after we have collected the data, we will test whether we did have some issues of common method variances. Okay, so here are the remedies. Ex ante is before you collect data, before you collect the data, right? The ex post is after data collection. There you go. You can avoid double barrel questions. You learn this in research methods as well. Appropriate sampling frame, improve scale items, reduce apprehension, protect respondents' anonymity. So you can say that the remedies before data collection are these, and the remedies after data collection are what? Okay, you can also include that in your proposal, or sorry, not in your proposal, in your thesis. Okay. Okay, so Hammond single factor is when we force everything into a single factor, right? Uses EFA, where all variables are loaded into a single factor and constrain the analysis so that there is no rotation. There's not going to be any rotation. We're going to talk more about rotation later on in factor analysis. If the newly introduced common latent factor explains more than 50% of the variance, then we have a common method bias, right? So I'm going to show you an example of it. So we're still using the same survey data. For example, under the survey data, we have optimism and mastery, right? We have optimism and mastery. We also have PANAS scale, the personality scale. We also have life satisfaction. So in this example, I'm just going to do optimism and mastery and also life satisfaction. So what do we do here? you go to dimension reduction, you go to factor, right? So you would include all these items here: optimism, mastery, and life satisfaction. In this example, just imagine that I only have 3 variables. I'm going to say optimism and mastery significantly influence life satisfaction. But if you have more than 3 skills, if you have more than 3 variables, if you have more than 2 variables, you must include every variable. All right, you have to include every variable. Okay, so and then you go to extraction, ensure that it's principal component. Okay, and analyze correlation matrix, display unrotated factor solution. Right, because we want to force it into an eigenvalue of 1. Just click OK. So you're going to look at this table over here. This is going to be different from your slides, right? This is going to be a little bit different from your slides. Just take a look at the table here and take a look at factor number 1. The component is also known as factor. Okay, factor number 1, is it more than 50%? It's not, right? It's not more than 50%. So we don't have an issue of common method bias. So this is how you report for CMV. The principal component analysis without rotation was applied on all measurement items. The result showed on all measurement items, okay? The result showed only 23%. In our case, it's not 23%. This is the old example. So in our case, how much, what's the percentage? It's 34, okay, 34%. 34.4% of the variance loaded on a single factor. Since 34.4 does not account nearly half of the variance extracted in the principal component analysis, it is suggested that the data is free from common method bias. That's all. So isn't it easy for you guys to check for common method bias? So what are the strengths and weaknesses of this method? So it's simple, it's very easy, but it has some weaknesses. As with a lot of other statistical analysis, it comes with weaknesses and its own strength. So weaknesses, it doesn't identify the method's effects. It's insensitive. Method assumes a single source of bias. Rare to have a single factor, because it is very rare for you to have a single factor, okay? So there's no guidelines. The only heuristic given here is 50%. And large number of variables increases the chance for multiple common method factors to exist. Because if you have a lot of variables, then definitely you're going to see more than one factors, right? So those are the strengths and weaknesses, and that's how you conduct common method variance, or that's how you test for common method biases. I'll see you in our next slides. Thank you very much.